This is our unit on multiple contrasts, and the first part will be on omnibus effects, and then our next part will be on focused effects. And the first question is, what do I mean by multiple contrasts? Recall that we had a previous unit that I called a unit on simple contrasts, and in that unit we looked at making comparisons between just two groups. Say we had a treatment group and a control group, and we wanted to see if there was a difference between those two groups on some outcome variables. For example, maybe levels of anxiety or levels of happiness. So now, in our unit on multiple contrasts, we're going to be looking at making comparisons between more than two groups. Maybe we have 3 groups, or 4 groups, or 5 or more groups. And here is an example that I think might be especially appropriate, given that we're getting near to the end of our statistics class. And one thing that often happens at the near to the end of a statistics class is that students start feeling sad because they think about, what will life be like if I don't have statistics class, and if I don't have statistics tests and statistics quizzes? It feels very sad to think about life without statistics. And I call this type of sadness statectomy sadness, the sadness caused by the removal of statistics. So when you start thinking about life after a statistics class and think about how sad you might feel because you don't have that class, we can call that statectomy sadness. And so say I wanted to do a study and test some different treatments that might make people feel better, that might help relieve the statectomy sadness. And one of the treatments would be this lavender buds, rose petals, and eucalyptus oil therapy, kind of an aroma therapy approach, where I would take some people that have just finished their statistics course and they're feeling very sad because they have no more statistics, and I put them in a room where they can smell some of these nice, wonderful fragrances and smells, the lavender buds and rose petals and fragrances, and maybe those nice smells will make them feel better. And then let's say I have a second treatment that's a very different approach, maybe kind of a paradoxical approach. The idea that if I give someone something really bad after they experience this bad thing, everything else will feel better. And so if they experience something bad, then after that, they'll feel better about not having statistics. And so I call the second treatment the aroma, Clorox, and coffee therapy, where maybe first they can smell some kind of Clorox bleachy smells, and maybe then they smell some ammonia smells, and then they drink some coffee, and putting all these things together, maybe that feel really bad. But well, now that I think about it, maybe life without statistics isn't so bad after all. So you know what? Actually, now I'm feeling better. So maybe some kind of this paradoxical approach, if you experience these noxious smells and drink coffee, that after you're through with all of that, you might feel better about not having statistics. Now, of course, don't try. I think that's actually dangerous. So actually don't mix Clorox and ammonia. I believe that's a very dangerous thing to do. But for my example, say I have this ammonia, Clorox, and coffee therapy as my second treatment. So I have 2 different types of treatments that I want to try out. I have this lavender buds treatment and this paradoxical ammonia and Clorox and coffee treatment. And then maybe I want to compare those 2 treatments to a control group. And for this control group, I'm going to have them do a treatment that I think is supposed to be inert. I think it's not supposed to have any effect at all. And so I have this, what I call my drinking glass, red stapler, and wood block therapy. I bring people in, and you experience the red stapler and the drinking glass and the wood block, and you kind of wonder what you're doing there and why you're there, what the whole purpose is, but it's really not for anything because you're just the control group, but you don't know that. So I have 3 groups, students that are experiencing the statectomy sadness, and people get randomly assigned. So some people get randomly assigned to the lavender buds treatment. Some people get randomly assigned to this paradoxical ammonia, Clorox, and coffee therapy. And a third group of people get randomly assigned to the control group, where they just simply experience a drinking glass and red stapler and a wood block, and nothing else happens. So in this hypothetical example, I want to see, is there a difference between these 3 groups? I have 2 different types of treatments and 1 control group, so I have 3 groups altogether, and I want to see, is there a difference between these 3 groups? So when I make comparisons between more than 2 groups, there's 2 basic types of questions that I can address. One type of question is a focused question, And another type of question is an omnibus question. We've talked about the difference between focused and omnibus questions before. Recall that a focused question is a question you can address with two hands. It's looking at a relationship between two variables or a comparison between two groups. So if I have two groups and I want to say, is the mean on an outcome variable for group A different from group B, that would be addressing a focused question. And when I make a comparison between, if I have two groups, and I'm going to make a comparison between those two groups to see if there's a difference in their means, if I'm looking at an outcome like happiness to see if the two groups have different levels of happiness. Or if I'm looking at an outcome like statectomy sadness, and I want to see if there's a difference between my two groups in levels of statectomy sadness. Or if I'm looking for treatments for allergies, and I want to see if there's a difference between my two groups in levels of allergy symptoms. Whatever it is, if I'm comparing two groups to see if there's a difference in the means between two groups on some outcome variable, that comparison is called a contrast. So a contrast is any time I'm going to compare the means for two groups, and a contrast addresses a focused question. So if I'm making a contrast, it means I'm comparing two groups, and it means I'm addressing a focused question. And if you think about it, note that I said that this unit is a unit on multiple contrasts, and that's because we're going to be talking about how we make comparisons when we have more than two groups. And to make that comparison, it means we're going to need to make more than just a single contrast. So when we have more than two groups, we start needing to make multiple contrasts, multiple pairwise comparisons between groups. So for example, if I have three groups, say I'm treating statectomy sadness, and I have the aromatherapy group that was exposed to pleasant smells, and then I have that paradoxical Clorox and coffee group that was exposed to noxious stuff, and then I have my red stapler control group that was exposed to inert objects. So if I have those three different treatment groups, people were randomly assigned to these three different treatment groups, and I'm looking for differences between these three groups in levels of statectomy sadness. That's my outcome variable. There's, in this case, with three groups, there's three different focused questions I could address, or three different contrasts I could make here. I could compare, for example, my control group, that red stapler group. I could compare the control group with the aromatherapy group to see if there's a difference. So I could say, if I say my control group is, say, group 1 and the aromatherapy group's group 2, I could compare the mean on the outcome variable y for group 1 minus the mean on the outcome variable for group 2 and get the difference between those two means, and that would be a contrast, seeing if there's a difference between my control group and the aromatherapy group. Or I could compare the paradoxical, the noxious Clorox and coffee group with the control group to see if there's a difference between those two groups. So in this case, if my control group is group 1 and say the Clorox group is group 3, in this case I'd be comparing the mean on the outcome variable y for group 1 minus the mean on the outcome variable for group 3 to see if there's a difference between the means for the control group versus the Clorox noxious paradoxical treatment group. Or third, I could see, is there a difference between my two treatment groups? Is the aromatherapy group different from the Clorox group in levels of statectomy sadness? So I can compare the mean statectomy sadness for if my aromatherapy group is group 2, so y bar for group 2 would be the mean statectomy sadness level for group 2 after they completed therapy. And then I have y bar for group 3. This would be the average level of statectomy sadness for people after completing the Clorox therapy. And I could see if there's a difference between my two treatment groups. And so I have three different contrasts I could make in the situation. And if I had more than three groups, then I'd have several more than three contrasts that I can make. But if I have just three groups, it turns out there's these three different contrasts that I can make. And each one of these contrasts would be a separate focused question. So I have three different focused questions I could look at. And the other type of question we can address when we're making comparisons between more than two groups is an omnibus question. And the omnibus question is the one that we need more than two hands to address. In this case, if I have 3 groups or 4 groups or 5 groups, I need more than 2 hands to hold all those groups. And the omnibus question is going to ask, in general, if I look at all those groups together, in general, is there a difference between those groups in their mean levels on some outcome variable? So if I have, say I have 2 different treatments for statectomy sadness plus a control group, so I have 3 different groups, and I want to know, is there a difference between those 3 groups in their mean levels of statectomy sadness after everyone's completed their treatments? That would be asking an omnibus question. That is, if I want to know in general, is there a difference between my 3 groups? That's looking at the omnibus question. And part 1 for this unit will focus on how we address the omnibus question. And then after that, part 2 for this unit will look at how we address focused questions. Now, recall from our previous unit on multiple regression, recall that in that unit we addressed an omnibus question as well. In that case, we had regression equations where an outcome variable was predicted with multiple predictors. We had multiple x variables. And when we asked the question, how much variance in the outcome variable y is explained by all of our predictors taken together, how much variance is explained by all the x's taken together, that was addressing the omnibus question. And recall that we addressed that by calculating a multiple correlation squared. Our capital R squared was the effect size that addressed that question. It told us how much variance in y was explained by all the predictors taken together. And we're going to do a very similar thing here, except for now we're going to be talking about contrasts. And I just defined what a contrast was. It's where we make a comparison between 2 groups. And if I just had 2 groups, when I make a simple contrast, we can ask the question, how much variance in an outcome variable y is explained by that contrast, by the difference between those 2 groups? And the thing is that if I have more than 2 groups, then I have more than 2 contrasts. So now the omnibus question is going to be, how much variance in y is explained by all the contrasts taken together? Looking at all the contrasts that I can do, all the different comparisons I can make between groups, how much variance in y is explained by all the contrasts taken together? In other words, the omnibus question, how much variance in y, is explained by multiple group contrasts. We're going to have more than just a single contrast to explain variance in y. And then that will tell us essentially, in general, is there a difference between groups? If I have 3, 4, 5 groups, if I have more than 2 groups, I'm going to ask this general question, is there a difference between groups? Technically, what we're asking is, how much variance in y is explained by all the contrasts taken together, all the contrast I can make? And the way that I answer this omnibus question when I'm making comparisons between more than 2 groups is very similar to how we answered the omnibus question when we were doing multiple regression. We're just going to make a little bit of a tweak to our approach. So let's see how this works. So recall when we were doing regression, we had an x variable was our predictor and y was the outcome. And we talked about how we can have a regression equation that plots out a slope, a line, where we say y is equal to intercept plus slope times x plus error. And that defines this regression line here. And our x variable is something that's numerically scaled. It ranges from low to high. So it could be a 1 or a 1.5 or 2. It could be anywhere along this number line here. And with this equation, we have this numerically scaled x variable that ranges from low to high. And we plug in our equation, we get the slope, and the slope gives us our predicted scores on y. So we use someone's score on x to get what their predicted score is on y. And the slope is what gives us what their predicted score is. Now, when I'm making group contrasts, my x variable is no longer a numerically scaled variable that ranges from low to high, but now x is going to be a categorical variable that represents group membership. It could be maybe I have 3 groups. Maybe it's the aromatherapy group and the noxious Clorox treatment group and the control group. Maybe I have 3 different groups. And so what group you're in, are you in group 1, group 2, or group 3? That's your x variable, and it's now a categorical variable indicating group membership. And then the outcome variable would say be your score on levels of happiness after treatment. And when I have a categorical X variable, when I'm making multiple group contrasts and I have more than 2 groups, and so X is categorical, we can take a shortcut to getting predicted scores on Y. We actually don't have to plug in that regression equation, although we'll see later on, we actually could and it will still work. But a shortcut we can take is simply whatever your group mean is, that's your predicted score for Y. So here I have this example where I have 3 groups, and group 1 had these 4 people in it: Antigone, Rufus, Eep, and Matilda. And group 2 had Oswald, Orgel, Gertrude, and Bruno. And group 3 had Ooze, Mafani, Fritz, and Og Hickey. So I have 3 different groups. And maybe I'm measuring levels of statectomy sadness in each group. And so these 4 people in group 1, their mean was a 10. And here I have these 4 people in group 2. Their mean score on statectomy sadness was a 35, so they were kind of distressed. They were feeling a lot of sadness and distress. And group 3 here, their mean on statectomy sadness was a 15, so they were in the middle of group. So group 1, I guess, would be the lowest, and group 2 was the highest, and group 3 was a little, just a smidgen higher than group 1. So I have the means for each group. And rather than going through all the work of calculating a intercept and slope in my regression equation, we can, at this point, we can just skip that and get to the predicted scores a lot easier, just knowing that whatever group you're in, your group mean is your predicted score. So everyone in group 1, Antigone, her predicted score is 10. She's in group 1. The mean for group 1 is 10. So Antigone's predicted score is right here at 10. Rufus, his predicted score right here at 10. Eep, his predicted score is right here at 10. Matilda, her predicted score is at 10. Everyone in group 1, that group mean is 10. So for everyone in group 1, their predicted score is 10. And in group 2, we have Oswald and Ugel and Gertrude. They're in a group that the mean for that group is a 35. So everyone in that group, their predicted score is 35. And group 3, the mean for that group is 15. So everyone in group 3, their predicted score is a 15. So when I'm doing multiple contrasts between more than 2 groups, I don't have to calculate regression slopes and intercepts. I can just get predicted values just by looking at what is the mean for everyone's group. And whatever group you're in, the mean for your group is your predicted score. And it's as simple as that. And recall from our previous unit on multiple regression that we addressed the Omnibus question by doing an analysis of variance. We used this ANOVA table right here, like what we're looking at. We used this table to address the Omnibus question. That is, we calculated an explained variance sums of squares, an error variance sums of squares, and a total variance sums of squares. And we put them in our table. So we put explained variance sums of squares, error variance, and total variance sums of squares. We put that in the table. And then we were able to use that. We took our explained variance sums of squares divided by total sums of squares to get the percent of variance explained. And that was our capital R squared. That was our effect size. And then we went on and used this table to calculate an F value, which is an inferential statistic used to test the significance of our effect size. And we're going to do all these same things here for this unit. We're going to just take what we talked about in our previous unit and plug it in here where we're talking about making multiple contrasts. And we're going to use this to address that omnibus question, that question of, in general, is there a difference between groups? Now, as we're doing this, there's a few places where some of the terminology is going to change. The math in the table will actually stay identical to what we had in our previous unit. But for whatever reason, when people talk about regression, they use one set of terms, and then when they talk about making group comparisons, they shift and use a slightly different set of terminology to talk about the exact same table. So, as we go along here, we'll need to change our terminology, even though the math in the table is staying the same as what it was in our previous unit. There's also a few points where I'll need to clarify a few things for how we apply this to a situation where I'm looking at groups. So let's see how we would apply this analysis of variance to a situation where I'm making comparisons between more than 2 groups. The first thing to calculate to do an analysis of variance, to fill in the values for our ANOVA table, is to calculate the error variance sums of squares. So how do we do that? Recall that when we were doing regression, we calculated a slope, and error was determined by the distance between someone's observed score and their predicted score. And the predicted score, what was given by the slope. So the slope determines what people's predicted scores are, and then for each person we look at what do they actually observe, how far did their observed score deviate away from that slope, away from that predicted score, and that was the error. So now when we're making group comparisons, it gets a lot easier to calculate error, because now we don't need to calculate slopes to get predicted scores, because group means now give predicted scores. Whatever group someone is in, the mean for that group is that person's predicted score. So here we have everyone in group 1, Antigone, Rufus, Eep, and Matilda, and the mean for group 1 is 10. So for everyone in that group, their predicted score is 10. Antigone actually scored 20. Maybe we're looking at statectomy sadness. So she was a little bit higher than the rest of the group. She scored a 20, but the predicted score for Antigone would be 10 because she's in group 1. Rufus, his sadness was down here at a 5, but again, he's in group 1, so his predicted score would be a 10. So we made Antigone's error would be 10 points above. Rufus's error would be a -5 because he's 5 points below his predicted score. Eep would have 0 error because his predicted score was the same as his observed score. So now, when I'm making group comparisons, error is the distance between an observed score and the group mean, because the group mean is simply the predicted score now. So error is still the distance between an observed score and predicted score. It's just that it's easier because the predicted score is simply the group mean. So it simplifies to error is the distance between observed score and the group mean. And when we're making group comparisons, I mentioned that people often use different language, and here's one of the places where the language is going to shift a bit. So I have up here error. That's the term we've been using, the distance between an observed score and predicted score, in this case group means. But error is also known as, aka also known as, within group variance. So this is a term that people use when they're making group comparisons. This term really wouldn't make sense if you're doing regression where you have numerically scaled predictors predicting an outcome. But when you're making group comparisons, this term makes sense because now error is the distance between observed scores and group means. So in other words, error is looking at the amount of variance that's occurring within each group. If people are deviating far away from group means, that means you have a lot of variance within groups, and that means you have high error. And if there's not much variance between people within a group, if everyone in a group is very similar, then that would mean you'd have a low group within group variance, and it would mean you have low error. So because error is the distance between observed scores and group means, it's essentially a measure of the amount of variance that's occurring. This is important, within a group. The within group variance is now what we're going to call error. So a switch in terminology here. We can still call it error, but the more common term is to call error the within group variance. And I have a note here, another term, and we've used this term before, but I'll make a note of it here again. We can also call error residual variance, and we've used that term before, so that's not a new term. So we can call error, can be called error, the error variance, or the within group variance, and that's going to be an especially popular term to use when you're doing group comparisons, or residual variance are all terms for the same thing. At this point, you might be able to guess how we're going to proceed to calculate the sum of the squared error. Let's take a look and see how this goes. So first, we need to calculate the error for each person in our study. And we were talking about this just a moment ago. So Antigone was 10 points above her predicted score, so her error is 10. Rufus was 5 points below. Up here we've got Oswald. He was 5 points above. Orgel was also 5. And we have Gertrude. She was 15 points below. Shows her sadness was only at a 20, but her predicted score was at 35 because she was in this middle group. So she was a lot lower than what we predicted. So her error was -15. Ooze was 5. Oghickey was 10 points above. Fritz was 5 points below, and so forth. So we'll calculate the error for each person, which is simply their observed score minus their group mean. which is the same thing as observed minus predicted. It's just that predicted simplifies to group mean. And then, as you might guess, we're going to take each of those errors and square it. So we'll take Antigone's error. She was 10 points above. We square it to get 100. Rufus was 5 points below. Negative 5 squared is 25, and so forth. So we'll just take each person's error and square it. So now we have squared errors. And then, as you might guess, we're simply going to sum all of our squared errors. We're going to add them up. So I've got Antigone plus Rufus plus Eve and so forth. So we've got all these people, just 12 people. And here I'm going to sum all 12 of their squared errors. And it turns out in this example, the sum of these squared errors adds up to 700. So our sum of squared error is 700. And recall, as I noted just a moment ago, we could call this the sum of the squared error. A more common term when you're making group comparisons is to switch our terminology and now call this the within group sum of squares. So we could call it sum of squared errors. Often people switch the terminology and now call this the within group sums of squares. So the within group sums of squares, aka also known as the error sums of squares, in this example is 700. And the next step is to calculate the total variance sums of squares. And once again, we're going to do this just like we've done before in the past. So the total variance sums of squares is going to involve how far people deviate from what I'll call the grand mean. And I'll differentiate a grand mean from the group means. So just a moment ago, when I was talking about error variance sums of squares, we talked about how each group has its own mean, and I'll call those the group means. And everyone in group 1, the mean for group 1 was 10, so that was the predicted score for everyone in group 1. And group 2, the mean for group 2 was 35, so everyone in group 2, their predicted score was 35. And so when we're doing group comparisons like this, it's helpful to clarify and distinguish between, are we talking about a group mean, which is just the mean for a single group, or the grand mean, which is the mean for everybody. So I'm going to use that language to make sure we're clear about which type of mean we're talking about. So the grand mean is the term I will use when I'm talking about the mean for everyone in the group altogether. So if I take all 12 of these people, add up their scores, divide by 12 to get the average score for the entire group, my grand mean is 20. And I've drawn this red line right here at 20 to show that's the grand mean. And here is the formula for calculating a total variance sums of squares. And that's just the same formula we've seen before. In fact, go back to our very first unit when we were talking about standard deviations, and we talked about calculating a sum of squares, which was a sum of x minus x bar squared, and we summed that up to get our total sums of squares, which was the first step of calculating a standard deviation. And now I've switched, and rather than x's, I'm talking about y's, and this is because we're looking at an outcome variable. We've got group membership as essentially our predictors. We're essentially trying to explain or predict variance in y given group membership. And so our outcome variable, say it's levels of statectomy sadness, we'll call that y. And so we're looking at how far each score deviates from the grand mean. And just to clarify, I've put in the subscript grand here. I didn't use that word in previous formulas just because I didn't need to clarify then. But now I want to make sure we're clear about if we're talking about group means or grand means. So I put the word grand here to clarify. I'm talking about the grand mean. And I actually put this in bold font, which is also another typical thing that people often do to clarify when we're talking about a grand mean. So this is the same formula that we've seen before. I'm just clarifying that it's a grand mean. So each score on the outcome variable y minus the grand mean of y, take observed minus the grand mean squared and summed up for everyone in our sample, and that will give us our total sums of squares, which is what we need for our ANOVA table. If we wanted to, we could divide that by our degrees of freedom and we would have a variance, and if we take the square root of that, we would have a standard deviation. But for the ANOVA table, we just need these sums of squares. So here's what it looks like in our current example. I took each person's score and took how far they deviated from the grand mean and squared it. So for example, EAP was 10 points below the grand mean, and 10 squared gives me 100 and so forth. So I took each person's score, squared it, and then add up all these squared deviations, and my sum of squares for this example is 2,100. So 2,100 is my total sums of squares. And then finally, we need to calculate explained variance sums of squares. And just as in previous units, if at this point, if we've actually already calculated our total sums of squares, and if we've already calculated the error variance sums of squares, or which we're now calling the within group sums of squares, if we have both the total sums of squares and the error sums of squares, we can just take total minus error, and that will give us explained variance. And that was true when we were looking at regression, and that's still true here. So total minus error will give us explained variance. And that's one option for the way to calculate the explained variance sums of squares. And if we don't already have the total variance sums of squares and the error variance sums of squares, we can calculate our explained variance sums of squares from the ground up. In other words, this is option B for how to calculate the explained variance sums of squares. And this will use essentially the same formula that we used in our previous units on regression. Recall when we talked about regression that I defined the explained variance sums of squares, where we take someone's predicted score on an outcome, y hat, minus the mean for y hat, y minus y bar, and then we squared that and summed that up for everyone in the sample. So we took each person's score on y hat, their predicted score, minus the mean of y, squared and summed up. And when we were doing regression, that actually gave us a measure of how steep the slope was. It was a measure that told us that got a value that gets bigger when our effect size gets bigger, and it gets smaller when our effect size gets smaller. So now let's look at how this formula plays out. If I take each person's predicted score minus the mean, I'm going to clarify now, this is going to be the grand mean. So I'm going to get the predicted score minus the grand mean. And note that if I'm doing group comparisons, my predicted score is the group mean. So now I've got the predicted score given by the group mean minus the grand mean. And because everyone in the group will have the same group mean, this formula gets a little bit easier if I just take how far did this group mean deviate from the grand mean and then multiply it by the number of people in that group. So I could take how far for Antigone, how far her predicted score deviated from the grand score. I could take Antigone's score predicted minus the grand mean, and then Rufus predicted minus the grand mean, and then Eep predicted minus the grand mean, and then Matilda predicted minus the grand mean, and then add those all up for that group. But everyone in that group, their predicted score is 10 because they're in group 1. The mean for group 1 is 10. So everyone has the same predicted score. So predicted score minus the grand mean is the same for everyone in that group. So I could simplify that just to take this group mean minus grand mean times 4 times the number of people in that group, and that's an easier way to do it. And so for every group, I'll take the group mean minus the grand mean for group 1, and then I'm going to square that deviation and multiply it by the number of people in that group. And then for group 2, we'll take that group mean minus the grand mean squared, multiplied by the number of people in that group, and then we'll do that for each group. So this other option simplifies to the sum of the squared group deviation times the group sample size. That is, for each group, I take that group deviation, I square it, multiply it by the sample size, and then add that up for all my groups. And that's another way that I would calculate the explained variance sums of squares. As I just mentioned, the explained variance sums of squares is a value that's going to be related to the overall effect size. That is, if we have a big effect, then the explained variance sums of squares is going to be a larger value. And if we have a small effect, then the explained variance sums of squares is going to be a small value. In our previous units on regression, we saw how the explained variance sums of squares was related to the steepness of the slope. When we had a steeper slope, this value got larger, and as the slope got flatter, this value got smaller. Now it's going to be related to how far groups deviate from the grand mean. And note, this is a measure of the effect size. In other words, it's a measure of how much groups differ from each other. The more that groups differ from each other, then the more there's going to be differences between group means and the grand mean. If there's no differences between groups, then they will all have the same mean, and that same mean will be the grand mean. That all the groups will have the mean that is the same as the grand mean if there's no differences between groups. So explained variance is related to the distance between group means and grand means. The more there's distance between group means and grand means, the more there's differences between groups, which means we have a larger effect, a larger amount of differences between groups. If all groups have the same mean, then that would mean that there's no differences between groups and that they would all have the same mean, they would share the same mean, which is the same as the grand mean. And so if we have lots of differences between groups, a lot of differences between group means and grand means, then our explained variance will be a higher value. And if all groups have the same mean, or they come close to having the same mean, then our explained variance will be smaller. And if they all had exactly the same mean, then there would be no explained variance whatsoever. Another term for the explained variance sum of squares is to call it the treatment effects. I might have used that term before. This term makes a whole lot of sense if you're thinking in terms of doing an experiment where you're randomly assigning people to treatment groups and control groups. And so if you're thinking in terms of experiments, it makes sense to call your explained variance sum of squares treatment effects. And when people are doing group comparisons, one of the most common places where you do group comparisons is where you're doing an experiment where you've assigned people to treatment and control groups. So oftentimes when people do group comparisons, it's common to use the term treatment effects. And an even more common term is to call your explained variance sums of squares the between groups variance, because we're looking at how far groups differ from each other, or how far groups differ from the grand mean. So it's a measure of how much differences there are between groups. So they call the explained variance the between groups variance. So this gives us a pair of terms for error variance and explained variance in terms of groups. We can call the error variance, we saw just a moment ago, the error variance was the within group variance, and now the explained variance is the between group variance. And these are very common terms to use when people are doing group comparisons. So rather than talking about error variance and explained variance, it's much more common to talk about within group variance and between group variance. Within group variance is the error variance, is the within group variance, and the explained variance is the between group variance. So let's add this up for our current example. So here's group 1, and group 1 was 10 points below the grand mean. The mean for group 1 was a 10. The grand mean was 20, so group 1 was negative 10. That's how far they deviated below the grand mean. Group 2, their deviation is 15. The grand mean was 20. The mean for group 2 was 35, so they're 15 points above the grand mean, so their deviation is 15. Group 3 was 5 points below the grand mean, so their mean score was negative 5. So we have a deviation score for each group, negative 10, 15, negative 5 is how far each group mean deviated from the grand mean. And now I'm simply going to square those deviations. So the squared deviation for group 1 is 100. The squared deviation for group 2, 225. And group 3, they were 5 points below, 5 squared. I get 25. So I have the squared deviation for each group. And then finally, I'm going to take each squared deviation and multiply it by the number of people in the group. So group 1, their squared deviation was 100. There were 4 people in that group, so I take 100 times 4. Plus group 2, their squared deviation was 225. Again, 4 people in that group, so 225 times 4. And group 3, their squared deviation was 25. 4 people in that group again, so 25 times 4. And add up all of those, I get 1,400. So our explained variance sums of squares in this example is 1,400. Now, let me summarize the equations we used to calculate explained variance, total variance, and error variance sums of squares. So we just calculated, just now, we calculated the explained variance sums of squares. And our equation for the explained variance sums of squares, or I could say sums of squares treatment, or I could say sums of squares between groups. So sums of squares treatment, sums of squares between groups, sums of squares, explain variance, all terms for the same thing, is the sum where I take each group mean minus the grand mean squared times the number of people in the group. And I sum that up across all groups. And that was how we calculated our explained variance, sums of squares. Explained variance between groups, treatment effects, sums of squares. And again, to review what we've been doing, for the error variance sums of squares, which is the same thing as the within group sums of squares, so the error variance sums of squares or the within group sums of squares, we simply took for each person, took their observed score minus the group mean, which was that person's predicted value, observed minus predicted, or observed minus group mean squared, and summed up for everyone in our sample. And that gave us the error variance sums of squares, which is the same thing as the within group sum of squares. And then finally, for our total variance sums of squares, we just took how far each person's observed score deviated from the grand mean and squared it and summed that up to get our total variance sums of squares. And so now we have all three types of sums of squares. We have our explained variance between groups sums of squares, our error variance within groups sums of squares, and our total variance sums of squares. And now we can plug these values in to our ANOVA table and do an analysis of variance. And we can use this table to calculate the percent of variance explained. And we can use this value to calculate an F statistic, which is our inferential statistic, to test the significance of our omnibus effect. Let's start by looking at how we would calculate that F statistic. And it's essentially going to be the same as we've done before. So we'll have our total variance sums of squares. We'll have our error variance sums of squares. And the only change here is that now, instead of calling it error, I'm more likely going to call it my within groups sums of squares. So I'm just changing the terms. Same means the same thing. It's just that now we're calling it within groups sums of squares. Our explained variance sums of squares, but now we're more likely to call it between groups. So again, we're just changing the names, but it means the same thing. So we have our between group sums of squares, our error sums of squares in total, and then we need to get our degrees of freedom and divide each sums of squares by degrees of freedom to get a mean square. Take mean square explained, that is mean square between groups, divided by mean squared error, that is mean squared within groups, and we'll have our F value. Now, one thing, if you recall from regression, I talked about how our degrees of freedom total was n-1. And when I talked about our error, which I'm now calling within groups degrees of freedom, but our error degrees of freedom, previously I said it was n minus number of predictors minus 1. And for our explained variance degrees of freedom, I call it number of predictors. And p was number of predictors. But what is p now? So now I'm going to say that p, I'm actually, as we'll see a little bit later on, it actually still is number of predictors. But before that can make sense, let's define it in a simpler way that will make sense for what we're doing right now. I'm going to say that p is simply the number of contrasts that are free to vary. So p, it actually still does mean number of predictors, but for right now it's easier to think of it as the number of contrasts that are free to vary. And then I have down at the bottom, which is, what do I mean by that? How many contrasts are free to vary? What do I mean? So let's see how we can figure out how many contrasts are free to vary. So to determine how many contrasts are free to vary, what we need to do is to first figure out how many contrasts are possible. That is, what is the total number of possible contrasts that we could make, and then determine how many of those are free to vary. For example, if I had three groups, if I have my aromatherapy group and my paradoxical Clorox and coffee group and my control group, bread stapler and drinking glass group, if I have three different groups, in this case, there's actually three different contrasts I could make. I could compare my control group with the aromatherapy group. That's one possible contrast. I could compare the control group with the Clorox paradoxical Clorox coffee treatment group. That would be a second contrast I could make. And I could compare the two treatments with each other, the aromatherapy versus the Clorox group. So I have three possible contrasts that I could make. And the question is, if I have three possible contrasts, how many of those contrasts are free to vary? And to explain what I mean by that, I want to play that same game that, if you recall, way back when I defined degrees of freedom that we played at that point. So we'll take contrast 1, where I have the mean for the control group, and I don't know what it is, and the mean for, I'll call this group 2, will be my aromatherapy group, and I want to know what is the difference. What is the difference between these two groups, this contrast? The contrast for the control group versus the aromatherapy group, given by the mean for group 1 minus the mean for group 2. That's the size of difference between those two groups. What is that difference? And we'll play this game where I ask it like this. What does that difference have to be? And the answer is, well, it could be anything. There's no right or wrong answer to that. So this difference is free to vary. This is free to be anything. So that contrast could be anything. Now, say I know what it is. Say I know that my control group got a mean of 15 and the aromatherapy group had a mean of 10. So maybe I'm looking at the statectomy symptoms, how sad people felt. And so my control group had a sadness score of 15, and the aromatherapy had a statectomy sadness score of only 10. They were a little bit lower. And so the difference between those two groups, y1 minus y2, y bar 2, is 5. So there's 5 units of difference between those two groups. And so if that's known, and if I know that this group had a 15, I'll go ahead and plug that down here because I know that my control group had a 15, and I know my aromatherapy group had a score of 10, so I plug that in. And now let's ask the question, the second contrast for the control versus the Clorox group, what does that contrast have to be? Well, the answer is it could be anything. We don't know what it is, meaning it's free to vary. It could be anything. So at this point, we have two contrasts that are free to vary. This first contrast, that could be anything. And if that's known, the second contrast is still free to vary. But what if that's known? What if we know the results of the second contrast? What if we know that the Clorox group actually got a score of 35 was their mean score for that group? So now we know the results for this first contrast, know the results for the second contrast, and once we know that, this third contrast is not free to vary. Because in the process of making these first two contrasts, we figured out that the mean for the aromatherapy group, that was 10, so we already know that must be 10. And when we made the second contrast, we figured out that the mean for the Clorox group was 35, so we already know that. So this third contrast is not free to vary. So the number of we have 3 possible contrasts that we could make, but only 2 of them are free to vary. We have 2 contrasts that are free to vary. So as it turns out, the number of contrasts that are free to vary will always be equal to the number of groups you have minus 1. Whenever you're doing group contrasts, the number of contrasts that are free to vary will always be equal to number of groups minus 1. So if you have 3 groups, you will have 2 contrasts that are free to vary. If you had 5 groups, you would have 4 contrasts that are free to vary. And as I will show you later on, that this is actually the same thing as the number of predictors. Number of groups minus 1, or the number of contrasts that are free to vary, is actually going to be the same thing as the number of predictors in our equation. But we're not quite ready to talk about that yet. So for right now, just note that P in our degrees of freedom, n minus p minus 1, or in our explained variance is just p. Our p stands for number of contrasts that are free to vary, and that's going to be equal, p will be equal to the number of groups minus 1. And I have a note down here at the bottom that a lot of times in stats textbooks and places where people talk about analysis of variance, this formula for number of groups minus 1 is often notated as k minus 1, where k is number of groups. So they say the number of groups, number of contrasts that are free to vary is equal to k minus 1. It's a common way of notating this. And here is computer output for the example that we've been looking at for this unit. And note that because we're comparing groups, we're doing group comparisons, the computer has labeled our explained variance. It's given it the label between groups. And for the error variance, it's given it the label within groups. And so over here we have our column of sums of squares, and our explained variance between groups, sums of squares, was 1,400. That's what we calculated just a moment ago. And when we calculated our error variance, that is what we're now calling the within groups sums of squares, we got 700. And when we calculated our total sums of squares, we got 2,100. And so then to calculate our f, we take our sums of squares divided by degrees of freedom. And our total degrees of freedom is n minus 1. So we had 12 people in the sample. So 12 minus 1 is 11. And our within groups are error degrees of freedom. That's n minus p minus 1, where p is the number of predictors. We'll see that in just a moment here. Or the number of contrasts that are free to vary. And we have 3 groups. So we have 2 contrasts that are free to vary. Number of contrasts that are free to vary is equal to number of groups minus 1. So we have 2 contrasts free to vary. So n minus p minus 1, 12 minus 2 minus 1 gives us 9. And then the between groups degrees of freedom is simply p, which we'll see later is the number of predictors, or the number of contrasts that are free to vary is just 2. And as always, when we're looking at degrees of freedom, it adds up so that your explained variance plus error variance, or in this case what we're now calling between groups degrees of freedom plus within groups degrees of freedom, adds up to your total degrees of freedom. And then if you take sums of squares divided by degrees of freedom, you get the mean square. And then if you take mean square numerator, in this case we have 700, divided by mean square denominator, 77, we get our f statistic, which in this example comes out to a nice, neat f of 9. And then the computer has calculated our p-value for us. What's the probability of this f if the null hypothesis were true? That is, if we had no differences between groups at all. What's the probability of getting this size of an f value? Where the probability is 0.007, very, very small probability. So that would definitely be significant, and we would reject the null hypothesis and claim that we have a significant effect. Now, one key question is, what is the effect size? We haven't looked at how we would calculate that effect size yet, and we'll do that in just a moment. But before we do, I want to call attention to a few things in this ANOVA table that we can calculate. As in previous units, I often like to give results of an ANOVA table, then ask you to calculate things based on what's in that table. So for example, given results of this table, as before, we could calculate the standard deviation of the outcome variable y. The standard deviation of y is equal to the sums of squares divided by degrees of freedom. And we have the sums of squares of y right here, and we have the degrees of freedom right there. So 2,100 divided by 11 would give us the variance. And if we take the square root of that, we would have our standard deviation. So we have a standard deviation of 13.817. And as we're thinking about that, maybe go back and review or think about that googly-eyed sheep table and all the different types of distributions we talked about. And recall that this standard deviation is answering a type of question where we say observations of what, deviations around what. It's observations of people and how far people deviate from a group mean. So on average, for example, in this, if we're looking at an outcome variable that's levels of statectomy sadness, of how sad people feel, that we have a standard deviation of 13.81, meaning on average, people in our sample deviate, almost 14 points from the group mean. People's actual level of statectomy sadness deviates on average about 14 points, almost 14 points from the group mean. And we can get that standard deviation from our ANOVA table by looking at the sums of squares total divided by degrees of freedom to get our variance, then take the square root, and we have our standard deviation. And another value that I sometimes ask you to calculate from an ANOVA table is the standard error of estimate. Recall that whereas the standard deviation tells you how far on average people deviate from the sample mean, the standard error of estimate tells you how far on average people deviate from their predicted values. Again, standard deviation, how far on average people's scores deviate from the sample mean. Standard error of estimate, how far people's scores typically deviate from their predicted values. And as always, we can calculate the standard error of estimate simply by taking the square root of our mean squared error, or what we're now calling the mean square within groups. Because our formula for the standard error of estimate, which is given right here, we take the sum of the squared error, y minus y hat squared, and that's this value right here, 700 is our sum of squared error, divided by our degrees of freedom, which is given right here. 9 is going to be our degrees of freedom, to get our mean squared error. That's how far people's squared values typically, or the squared error that we get, the typical distance that people's observed scores deviate from their predicted scores in squared units. And then if we take the square root of that, we will have our standard error of estimate, how far people's observed scores typically deviate from their predicted values. And if we do that with this sample, we get a standard error of estimate of 8.81. That's almost 9. So in other words, when we use group membership to try to predict people's levels of statectomy sadness, we usually make about 8 or 9 units of error in trying to predict people's scores. We're usually off by almost 9 points in predicting people's level of statectomy sadness. So we looked at how we can calculate both the standard deviation and the standard error of estimate looking at results from this ANOVA table. Standard deviation, how far observed scores typically deviate from the sample mean. Standard error of estimate, how far observed scores typically deviate from their predicted values. Now, I've been calling this value the standard error of estimate. You take the square root of your mean squared error. It tells you how far on average people deviate from the predicted values, and that is the standard error of estimate. And that's a perfectly reasonable and valid term to use. And when people are doing regression, that is the term they always use. But when people are making group comparisons, this is another place where the terminology will change, because when people are making group comparisons, they almost never call this value the standard error of estimate. If they take the square root of the mean squared error, technically it's accurate to call that the standard error of estimate, but when people are doing group comparisons, they call it something else. Can you think about what term might be appropriate for what we get when we take the square root of the standard of the mean square within groups? What else is this? What else is a square root of the mean squared error? So we just calculated a standard error of estimate, and we saw that the value was 8.819. And I'm asking the question, what else is this? What is another thing we could call the standard error of estimate? And when we're doing group comparisons, the standard error of estimate is the same thing as the pooled within group standard deviation. Standard error of estimate is the same thing as a pooled within group standard deviation. And when people do group comparisons, they almost never call it the standard error of estimate. Instead, they always use the term pooled within group standard deviation. What do I mean by that? So when we talk about the standard error of estimate, it's looking at how far people's observed scores deviate from the predicted scores. Here I have y minus y hat, observed minus predicted. So when we're looking at the standard error of estimate, it's saying what's the average size of this deviation? How far on average do observed scores deviate from predicted scores? Then recall that because we're doing group comparisons, people's predicted scores are the same thing as their group means. So asking the question, how far do observed scores deviate from predicted scores, is the same thing as asking how far do observed scores deviate from group means. And if you want to know how far on average do observed scores deviate from group means, that's asking about a type of standard deviation. Now, this isn't the total standard deviation. It's not the standard deviation we looked at just a moment ago, which was how far people's observed scores deviate from the grand mean, but this is the within group standard deviation, how far their observed scores deviate from their group means. So the standard error of estimate, when we're doing group comparisons, the standard error of estimate tells us how far people's observed scores deviate from predicted scores, which is the same thing as how far observed scores deviate from group means, which is a type of standard deviation. In this case, it's the pooled, that is, we're looking at across on average across all three groups, pooled across all groups. What is the pooled within group standard deviation? Same thing as a standard error of estimate. And when you're doing group comparisons, the more common term to use is to call this thing the pooled within group standard deviation. And now we're ready to calculate an effect size for our omnibus effect. And we're going to do the exact same thing that we did when we were calculating an effect size for the omnibus effect in multiple regression. But once again, we're going to change the terminology. So if you recall from our unit on multiple regression, when I wanted to get that omnibus effect size, that is, what's the effect of all my predictors taken together, we took the total sums of squares explained variance divided by the sums of squares total from our ANOVA table, took sums of squares explained divided by sums of squares total to get the percent of variance explained. And so now, to get the effect size for our omnibus effect, if I have more than 2 groups and I want to find out if there's a difference between groups, if in general there's a difference between groups, what percent of variance in Y is explained by all the possible contrasts that I can make, what's the total percent of variance explained by group membership, I will do the exact same thing. I'll go to the ANOVA table, get my sums of squares explained, divided by sums of squares total. That will give me percent of variance explained, just like it did when I was doing regression. But we're going to change the terminology. For reasons I'm not clear on, for some reason, when people do regression and calculate the percent of variance explained, we call it R squared. That's what we've been doing. Capital R squared is the percent of variance explained when you're doing regression. But when you're doing group comparisons, for some reason, people decided, let's call that eta squared. That is, we'll take that Greek letter eta and use eta squared will be the symbol for percent of variance explained from an ANOVA table when we're doing group comparisons. So if you take sums of squares explained divided by sums of squares total from an ANOVA table, that will always give you percent of variance explained. But if you're doing regression, we'll call that percent of variance explained capital R squared. And if you're doing group comparisons, we'll call that percent of variance explained eta squared. Same exact mathematical formula, same exact thing, just for some reason, 2 different names depending on whether you're doing regression or group comparisons. So now we have the effect size. So if you want to answer that omnibus question, if you have 2 or more groups and you want to know what's the total percent of variance in Y that's explained by group membership, that is, what's the total percent of variance in Y that's explained by all the possible contrasts you could make between groups, your effect size that answers that omnibus question that gives you the total percent of variance explained by group membership, your effect size will be eta squared, which is analogous to, well, really the same thing as R squared. And as we saw just a moment ago, your inferential statistic will be the F test. So our eta squared will give us a percent of variance explained. That will be our effect size. Our inferential statistic that will test the significance of our eta squared will be the F test. And also finally, I want to note that just like capital R squared, just like our multiple correlation, the eta squared is a biased statistic. That is, both of these are statistics that if you were to do a study and then replicate your study and then replicate your study and do it over and over and over again an infinite number of times, the average of all your statistics, so the average of all your R squareds or the average of all your eta squareds will not exactly equal the true population parameter. These statistics will slightly overestimate that true population parameter. So both R squared and eta squared are biased statistics, meaning that when you run a study, your results are likely to be slightly higher on average. If you replicate your study over and over and over again an infinite number of times, on average, your statistics that you got from your studies will be slightly higher than the true population parameter. Now, I mentioned that both R squared and eta squared, which are 2 versions of the exact same statistic, I mentioned that they're both biased. And one thing that strikes me as somewhat of an interesting, maybe call it a cultural difference between researchers who do a lot of group comparisons, researchers that do a lot of experiments where they're making group comparisons, compared to researchers that do a lot of regression analysis, is that for some reason, researchers doing group comparisons tend to be especially concerned about bias. And so whereas the capital R squared is a biased statistic, people often look at R squared and say, well, we know it's biased, but we're not going to worry about it. We can make some corrections, but typically people don't. But for eta squared, it's more common for people to want to make a correction to try to correct for the bias. So for whatever reason, both R squared and eta squared, we can make corrections to try to get an unbiased estimate of the statistic. But for some reason, people often don't bother to correct the capital R squared. They just know it's biased and keep that in mind when they interpret it, but they don't bother to try to correct for that bias. Whereas when people get an estimate of eta squared, they're more likely to want to correct for that bias and get a better estimate of what that effect size is after accounting for the bias. And a common formula for doing that is this thing called omega squared. There's actually many different formulas, and some of them work better than others. I don't think any of these formulas work totally perfectly. But omega squared is probably one of the most common corrections that people can make to an eta squared to transform it into omega squared, which gives us a bias-corrected estimate of the effect size, a bias-corrected estimate of the percent of variance explained. It gives us an estimate that's much less biased than is eta squared. Eta squared by itself isn't really all that biased, but omega squared is much less so. And here's the formula for omega squared. It's not something I'm going to ask you to memorize, but you should be able to plug it in and use it if you needed to. So we need from our ANOVA table, we need to know the sum of squared explained variance, the degrees of freedom for our explained variance, and the mean squared error. And we take sum of squared explained minus degrees of freedom explained times mean squared error. And then we divide that by our total sum of squares plus mean squared error. So these are just values you would pull in from your ANOVA table. And the main thing I want you to be able to do is to recognize this is omega squared. This is a formula for omega squared. And it's a different way of calculating the percent of variance explained. So just like eta squared is going to estimate the percent of variance explained, the difference is that omega squared will give you a value that's been largely, not entirely, but to the best extent possible, it will give you a value that's been corrected for that bias. So omega squared is a much less biased statistic, an unbiased or almost unbiased estimate of the percent of variance explained. And when people do group comparisons, it's probably more common for them to report omega squared rather than eta squared. Whereas when people do regression, they often just report the plain ordinary capital R squared, the percent of variance explained, and it could be that could be corrected as well, but it's less common to do so. And that is everything for Part A, or Part 1, of Unit 6.